Hi, this is Professor Cummings, and this is going to be a video going into abrasive machining. So we've moved on to chapter 26 in your textbook, and now we're going to go into abrasive machining. So it's still under machining, but now it's just abrasives. Now, one thing, just as a heads up, I do use the words abrasives or grinding quite a bit versus just straight machining, like with an insert or not. So just keep in mind, I'll probably bounce around, and you'll see that also in my slides. But make no mistake, it is abrasive machining. It does fall under the category of machining. So let's get started. So this is a hydraulic cylinder. And there are a few things I want you to keep in mind about a hydraulic cylinder. Mostly how it actually works. How it's designed, how it's put together, but really what it has to do in order to function. So when you think about a hydraulic cylinder, what you have here is the piston rod. You also have the piston itself. You've also got the barrel. And of course, you got inlet and outlet ports. So as the piston or the piston rod moves back and forth as a unit, or it's forced back and forth through an inlet port, causing it to actuate, the hydraulic fluid exits. And as the pump or whatever causes the fluid to come in the other way, it causes it to retract, going through the other port. The fluid go through the other port. Now, when this is happening, there's a few things about this design that I want you to think about, not from the design engineer standpoint, but more from the manufacturing engineering standpoint. So there's quite a few things that you have to keep in mind as far as how to actually achieve some of the needs of what's going on here. So one thing is all this motion back and forth, and the fact that you can't have leaks. You can't allow that fluid to leak past the rod, and exit the piston that way, or the cylinder that way. You also don't want it leaking past the other side of the cylinder, or the piston, on either side, because then you'd lose power. You also would lose a lot of motion. So what you have to know is that there is, number one, a lot of contact between these surfaces. There's metal to metal, or a lot of cases metal to metal. Granted, you do have seals, but there's metal to metal contact, and as a result, you've got to have a very tight fit between the bore and the piston. You also have to have a very straight fit in order for this thing to continue to travel. It has to be, very well aligned. So what it means is when you design this, as well as when you manufacture it, you've got to take those surfaces into account. These are high contact surfaces. So the designer has to know to point that out, but as the manufacturing engineer, you have to know how to achieve that, how to make that happen. So you got to deal with the fact that you got a sliding motion. That sliding motion with the seals in the middle and everything also is prone to a lot of wear. You've got motion between two surfaces. You're prone to heat. It could potentially bind if these aren't totally straight. So you need to control the surface finish. And so the design for a sliding surface, mechanical design standard is 32 microinches or 0.8 micrometers, as far as just what the surface roughness should be. Now, when we talk about roughness, we're really talking about those peaks and valleys versus the waviness, which is the contour of the whole surface. So you got to be able to manufacture something that has a surface that is capable of handling, all of these demands. So if we look at this, and start to consider, exactly what we're looking at, what it actually has to do, and what the consequences are, premature wear, malfunctions, generally not getting the output that you need, whatever that actuator is supposed to be doing, accomplishing. You need to come up with a manufacturing process that can achieve all those requirements. Again, remember, we're talking about 32 microinches or 0.8 micrometers. So what that does, you have to start narrowing down what manufacturing processes you're working with. Now, in this particular chart, just before we go on with it, You've got up here on the x-axis, well, it's on both the top and bottom, the x-axis, you've got micro inches and you've got micrometers, and RA is just a roughness nomenclature. And you've got a grade going from the roughest application, of 50 micrometers or 2,000 micro inches, all the way down to the smoothest surface, 0.5 micro inches and 0.012 micrometers. And you got what each application can do. So you got metal cutting, abrasives, casting, forming, and then other. All right, so this is the manufacturing process, and here is what they can achieve, or the scale for what they can achieve. And these bars is what that particular process is capable of. Now, look down here at this legend. You got the most common is in black, which is in the center, and gray is a less frequent. That's all they call it, is less frequent. So keep in mind, so if you have a standard process of, say, milling, this is generally what milling can do in the black. So start out with a surface from 250 or 6.3 micrometers, 250 micro inches, all the way down here to 0.8 micrometers to 32 micro inches. So generally you don't get much more smooth than that from a milling application, except for these rare occasions. Usually you've done something special in your process. There's something you had to do to actually achieve that. That's not the normal, the common process. So keep that in mind of how you read that chart. Now, keep that in mind as well as what we have to achieve. We have to be at, no more than 32 micro inches. So what processes does this eliminate? Or what process does this narrow us down to? Another way of looking at it. Now look at everything that can go from 32 microinches or smoother. And that basically, as far as a common process, that eliminates almost everything except for a couple of processes outside of the abrasives. You can do that with burnishing, and you can sort of achieve that with boring, if you're very careful, and you can get it under very special circumstances for all the rest. But the only one that can consistently achieve these goals are abrasives. So that's why abrasive machining is so important to us. So this is what we're going to be going through in this section, is trying to understand what goes into abrasive machining and what it is that you're hoping to accomplish through abrasive machining. So understanding some of the theory and the principles behind it. Other things you can look at is what type of tolerances you can get. Again, here we have different types of machining, or different types of processes, rough machining, standard machining, all the way down to lapping at the end, and what type of tolerances you can get out of each one. So keep in mind, when you're talking about standard machining, you're talking about plus or minus 5 thousandths, and this is in inches. And this is your relative cost. This is another lesson I want to talk to you about as far as manufacturing processes as well as designing. When you consider, the cost that comes with each one of these tolerances, your tolerances become tighter and tighter. This is what the cost goes up. So when I say, be careful with your dimensioning and not to, make them unnecessarily tight, this is why. You're essentially dictating both a process that the person is going to have to take, a grinding process, or as well as adding to the cost. So you can make a part go from $10 to $500 very, very easy because you decided to put a couple extra decimal places in. And when you think about this as far as a piston, hydraulic cylinder, for example, you also got to consider the type of fit you're expecting. When you're considering these tolerances, the smoothness, when you deal with a hydraulic cylinder, you're trying to get a very tight tolerance, but it still will have a clearance. So you do have to have a clearance, but you have to be very careful as to how tight that tolerance is going to have to be. And hence one of the reasons you need these very tight tolerances. Now if we were to consider this sliding surface on a hydraulic cylinder, we could probably achieve the tolerance with a very careful machining application, but we can't really get that surface finish very easily with it. So we will be looking at grinding, or abrasive machining as an overall. for this section. And abrasive machining, just, since I corrected myself, has a lot of different applications, a lot of different ways that it'll present itself. And sometimes it is grinding. In other applications, it could be abrasive flow machining, where you actually have a putty medium and a grit that actually does internal, metal removal. Then you got water jet, grit blasting, vibratory mass finishing, and then Blanchard grinding, which is another grinding application. So for what we're going to be looking at in this presentation, and the next presentation, will be just what's known as bonded abrasives. And they're called that way because instead of just having a free-flowing grit in a medium, such as abrasive flow or water jet abrasive, these are actually bonded. And sometimes it's bonded to a wheel, sometimes it's bonded to some sort of other odd shape, like these deburring tools or small grinding tools, but they are bonded to a surface. So they are a rigid grinding tool. And when we consider bonded abrasives, there's three important aspects that you need to take into account and be able to understand. One is the grain. Another one is the actual bond itself. So here the grain, also called the grit, the bond itself. And then there's another one here, the porosity. Now, when you think of the porosity, you think of, just space. It's just a clearance, but it's actually a very important, very crucial part of the abrasive machining process, or bonded abrasive process. So the grit, just to go through more of what that is. Again, like I said, the grit, it's just the mechanism that removes the metal. And that's all it is. And it's, fairly obvious when this applies, whether it's bonded abrasives or any other type of abrasive. It's the medium that's doing the work, or the mechanism that's doing the work. Then of course you've got the bond itself. So the bond is this, hatched out area in between that basically holds the grains together. It's what forms that shape. The grains are actually put into this bonding material. That's what holds it together, and that's what keeps you in the shape that you want. Now, it doesn't necessarily have to come in the form of a wheel, and it certainly doesn't have to come in the form of a straight wheel. Like we saw on the last slide, you can have all sorts of weird contours to be able to grit any kind of shape, or cut any kind of shape that you need. Belts, bits, wheels, whatnot. Then of course there's the porosity. Like I said, all that is a clearance. So again, the clearance just allows for space, the chip, or what's known as swarf, or coolant, to go in between the grit. So help flushing, help keeping the temperature controlled, like any other type of spacing. But it does have other type of benefits and reasons you want to hold on to something like that. Now, I want you to also look at this diagram and notice that between these grit, or the grains, you are removing metal, and it does show, that this metal is going in between each one of these grit, the same way it would as a flute or the gullets in a brooch, right? So there is a purpose to that. So let's go ahead and, like I just compared this to a machining, your traditional machining process. So let's go ahead and go with that analogy, and I want you to keep that in mind as we look at the next couple of slides. So like I said, I compared it to a traditional machining process. And when we look at this, as we've seen this diagram, tons of times, where you've got your tool, you've got your workpiece, and you got your chip being formed. Very similar to what's going on in the grinding process. A few differences, but fundamentally, it's pretty analogous processes. You're doing pretty much the same thing. You've got a work tool, which in this case would be the grit, going into the workpiece, and what is a chip, or what we typically call swarf, being removed from the material. Only it's being removed chip by chip, little bit by little bit. It also, as we go through this material, it goes through that entire spectrum of the stress strain diagram. Like we had looked at in the beginning, with our strength of materials little briefing in the beginning of the semester. It goes through the elastic deformation stage, in the early stages of the stress strain diagram, goes to plastic deformation. You remember that's where it doesn't come back. Then it goes through the strain hardening and ultimate fracture. And that's the same thing that happens in both of these applications. And this is as that grain starts to move across the workpiece. So in those respects, those are two very similar processes. Some of the other things that to see is just comparing the two. Grains, unlike a cutting tool, is irregular. There's no standard size. There's no consistent rake angles. There's no consistent clearing angles. There's no consistent shearing angles. You've got a grain that can have generally random shapes and spacing from one to the next. The grain typically has a negative rake angle. And I say typically meaning it is still random, but there's a lot of leaning into the workpiece to give you that negative 60 degrees. And they have all sorts of different peripheral positions. Like I said, they're spaced in all kinds of weird ways. And this one is the next more important one. They have a very high cutting speed compared to or surface speed compared to a cutting tool. Sometimes up to 4,000 to 6,000 feet per minute. And remember this, we're talking about that tangential speed as a tool rotates and comes instantaneously in contact with the material. All right. Some other things about, just the grit itself, or the, grit versus a cutting tool. They're significantly smaller. Again, we're talking about something the size of sand, versus, the actual cutting tool, which can be about the size of your nail in some cases. You also get a very small material removal rate. Your depth of cut is much, much smaller. Your velocity is higher, but since your depth of cut is so much smaller, you're getting a lot less material taken out, which increases your cycle time and also helps drive the cost of a grinding process higher than a machining process. And here's where I use that word swarf. The chips come off are called swarf as opposed to chips. Another difference. Another thing as far as cutting tools go, comparing the two, is a term called friability. Something we're going to go through a couple of different terms as far as wear, but this one is important as far as comparing a cutting tool to grinding. You expect your grains to actually break. You expect them to break down. That's called friability, when your grains actually break, and it exposes new edges. So this is one of the ways that the wheel keeps its sharpness, keeps its productivity. So as it goes through the workpiece, those grains actually break, expose new sharp edges, and that's how it keeps cutting consistently. Now, there are other ways that this wheel can lose its sharpness, and we'll go through that later. But friability, just to give you a visual, is the grain itself actually breaking. Now, when you look at this diagram, you've got the grain, you've got the bond, and you've got the porosity. They don't actually label that out. But you've got this thing that can wear in a few different ways. And one of the ways is through this grain fracture. So if this grain literally breaks, that is the friability, that tendency to actually break. And since these grains can be made from various materials, they don't all break the same way. They don't all have the same friability. So a material with a high friability, meaning it breaks very easily, which keeps exposing new cutting edges, is also a low strength material. Now, going back to the porosity, again, that's very essential. Again, that's only the space between the grit, and up to the bond. It allows for the swarf to come out as well as coolant to come in. So it helps regulate the temperature. Without it, if you don't have that, what you're going to do is you won't get the chips out. Number one, you won't be able to get a cut. And what you're going to do is effectively just rub the material. And when you're just rubbing material against material, you're generating heat. And when you just have that complete, that heat getting built up, you can actually start damaging or deforming your workpiece. And it is possible to burn something with a grinding wheel, actually burn the metal. Also, when it comes to the bond, the thing that actually holds everything together, that maintains the shape of the wheel or whatever it is that's being bonded to, that bond material, it just holds that shape together. And that's what gives you your geometry. And it also adds a certain amount of strength and toughness. Different types of bonding material can help you with, or or it's used in different applications because of its ability to be a little more resilient or a little harder in the process. So I'll tell you what, I'm going to hold off here, cut off at this point, and I'll pick everything up in the next video.